level for people in the back. You okay? Okay. So this is the first slide and my first time exiting from my program here so that I can do something for you here. So this is a website that Kristen pointed me to, which if you happen to be in need of a stopwatch while you're online, this is where you go, called Online Stopwatch. So let's start it up here. That was exciting. So, we all just traveled 10 seconds forward in time. There you have it, the physics of time travel. Thank you all for coming. Okay, maybe that was just a little bit glib, but we can unpack this a little bit and maybe say something a little more interesting than watching a counter go from 0 to 10. You all sort of went along with my statement that we all just traveled forward in time 10 seconds, but if we unpack that a little bit, objectively, what actually happened was we sat here watching numbers go from 0 to 10. And we may have each felt a duration of time, but I would guess that each person in this room probably felt that duration of time a little bit differently from other people in the room. So there's sort of the objective idea of time, where you watch some kind of counter, and then there's your subjective experience of time, and that may be two very different things. So kind of the point of that is we all sort of have an agreement. It's easy to talk about time, but then when you kind of drill down to it a little bit, it's not completely obvious what we're talking about when we talk about time. So let me go back to the slideshow here and give you my references out front. This is by no means original work of mine. I was reading a bunch of books for my time seminar, and these are the ones that I mainly drew on for this talk. A little bit of warning here is you'll notice a philosophy book there, and while this was advertised as the physics of time travel, there's probably almost going to be equal parts philosophy in this talk. These are more physicsy books here. So this is a quote from Augustine, just to show you that people have been wondering about time for a very long time. What then is time? I know well enough what it is, provided no one asks me. But if I am asked what it is and try to explain, I do not know. That pretty well summarizes my font of knowledge about time. So don't ask me what time is, although we'll venture some opinions in any case. This is a recent physicist, John Wheeler, and a little kind of concise statement that I think physicists would like. Time is nature's way to keep everything from happening at once. So from a physics point of view, time is involved in how we describe motion of objects, right? That's a lot of what physics is about. This graph represents some rocket that we shot up into the air, and at some time that we like to label our symbols here. This is time 1. Our rocket was on its way up, and it was at this altitude. At some later time 2, my rocket has started to come back down, and it's heading back towards the Earth. So we parameterize motion in terms of time. That's one of the main ways we use time in physics, keeping track of when events happen. When you can mark certain parts of the motion of an object, like a rocket that you shot up into the air. So everyone knows about Newton, I assume, who gave us our laws of physics that we teach in our Physics 1 class. And, if you had a high school physics class, I'm sure you talked about Newton. Newton talked a lot about time in his work, and he had a view of time that is called absolute time. So this is Newton. People were fairly wordy back in the day. Absolute time, true and mathematical, flows equably in itself and by its nature, and well, you can read all that. So what he's saying is that time is not some material substance. It's not like, you know, the material in this podium, but it's in a sense real. And time is a container. So it's the container in which we can place events, things that happen. So in his view of time, time does not depend on the events, but events depend on the existence of time. If this absolute time didn't exist in the universe, then we couldn't have things happen. So a lot of philosophers and some physicists object to Newton's view of time. Philosophers argue that this is not even a self-consistent, coherent notion. One of my colleagues in the Department of Physics and Astronomy, John Walston, who delights in saying bad things about Newton, paraphrased Newton's view of time as absolute time is the time compared to itself that flows uniformly except when it doesn't. So does Newton's absolute time make sense? So philosophers would put Newton in the category of realists about time. Time is some sort of real thing. Others would argue that time is an idealization. It's not real in any sense. It's just a purely subjective notion. One of the Greeks that argued for this idealism view was Zeno. And some of you may know Zeno from his paradox. So if you don't know Zeno's paradox, it's okay, if I want to walk from one end of this stage to the other, I first have to walk halfway, and then the remaining distance I have to walk halfway again, and then the remaining distance I have to walk halfway again, and there's an infinite number of halfway steps, and so I never get there. Okay. That's Zeno. He applies the same logic to time, so that 10-second interval that we all experience, he would say, okay, you first have to experience 5 seconds, and then you have to experience half of that, and then you have to experience half of that. And so there's an infinite number of steps for that time interval of 10 seconds, so you never get there, okay? And he uses this to argue that time can't be real. Well, I think since, my personal point of view is since the invention of calculus, we solved that problem of the infinite number of steps, and so I don't think that's an argument that I worry about. But there are other philosophers that use other kinds of arguments to argue that time is not a real thing, it's just a completely subjective thing. Another point of view that I personally like a little better than throwing it in the purely subjective category is called relationism, that it's a way of relating events to each other. That the relationships between the events are something you can claim to be real. And then they're sort of agnostic on whether time itself might be real. So it kind of flips around Newton's point of view. Newton's point of view was time exists and you put events in it. And this point of view is events exist and we can talk about time with respect to events. Aristotle was someone you may have heard of who thought this way. Leibniz was a contemporary of Newton who would argue with Newton about absolutely everything, and this is one of the things he would argue with Newton about. So let's kind of go back to objective time or empirical time or measurable time. How do we actually measure time? Well, typically we measure time by looking at something that repeats itself and counting the number of times it repeats itself. So the motion of the sun, the motion of the moon, this was the basis of early timekeeping in just about every civilization I'm aware of, okay? The sun comes up, the sun comes down. You can put a stick in the ground and see how the shadow of the sun is moving as the sun goes about its daily path. And then for longer periods of time, you can look at how many of those days it takes the moon to go from a full moon to a new moon back to a full moon. So nature supplies us with a lot of repetitive things, and we usually use those to measure time against. Then around, what was it, the 16th century, the Galileo and others noticed that a pendulum was kind of an interesting repeating motion that could be kind of controlled and set, and you could use a pendulum to mark off finer units of time than, you know, just watching when the sun was overhead. And so the pendulum clock became established as a method of keeping time, a regular repeating motion. More recently, in the 20th century, people discovered that quartz crystals vibrate at a certain frequency, and so they could get even more precise watches and clocks using the vibrations of quartz crystals. And that's what's going on in the watch I have on my wrist. And then for the super precise measurement of time, we now have these atomic clocks, which use the vibrations of cesium atoms. Zillions of times a second, your cesium atom will oscillate, so you can get incredibly fine measurements of time down to, you know, billionths or trillionths of a second. So our official US time comes from Colorado, the National Institute of Standards, and they have a website, time.gov. You can go there. I won't go there, but if you're really, you know, one of these people who wants to be absolutely precise about what time it is, it will even correct for the time it takes the signal to get from Colorado to your computer and tell you exactly what the official US time is right now. As Kristen alluded to, I've been around for a while. I've been around long enough that when I was a kid, I would call up this toll-free phone number that would give you the time. I see a few gray-haired people out there that may have done this in their youth. At the tone, the time will be 8 o'clock, and ding, and set your watch to it. You know, budding young physicist that I was, I would call this thing constantly on the way through setting my watch. Anyway, so sorry, let's go back. So let me get to Einstein now. So Einstein's special relativity is what I'm going to talk to you about next. In his theory of special relativity, light is a very special thing, and the speed of light is a special speed that, regardless of your motion relative to the light source, everyone sees the speed of light as the same. And this is weird if you think about it, right? Because if you think about normal objects like a car going down the street, if you're standing on the sidewalk, you would perceive the car to have a certain speed moving away from you. But if you're in another car going down the street at about the same speed, your perception of that car's speed would be very different. You would expect that to hold true for light coming from a laser pointer, right? But what Einstein says is the light coming from a laser pointer, whether I'm moving in a car down the street or whether I'm standing on the podium here, we get exactly the same value for the speed of light, regardless of its motion relative to us. And what that does is it messes with space and time and connects them, because what's a speed? A speed is a distance per unit time, right? So if I'm going to claim that everyone sees the same distance per unit time, then something weird has to either happen with the distance or something weird has to happen with the time, and it turns out something weird happens with both. So let's start with the something weird that happens to time, because that'll connect me to a form of time travel, which you all came here to hear a little something about time travel, so I'll give you a little something on this slide. So moving clocks run slow is what happens in Einstein's special relativity. So if I've got a clock moving in a rocket ship and I look at that clock, I think that clock is running slow. And for those of you who want to do some algebra, this is the formula that tells you what the time is that I see in the moving clock. This is the time when the clock's sitting still, and this is the speed that the clock's moving. C is Einstein's symbol for the speed of light. Okay, so if you care about the formula, go for it. If you don't care about the formula, the slogan is moving clocks run slow. Okay. So there's a perfectly easy way in special relativity to do time travel to the future. Okay. I mean, we talked about we time traveled to the future earlier at a rate of 1 second per second, right? When we were doing the clock going at 10 seconds. But here, if you wanted to skip a few centuries on Earth, all you have to do is get on a rocket ship, travel some distance, say to the nearest star at near light speed, turn around, come back at near light speed, and you'll find that you haven't aged very much, but centuries have passed on Earth. Okay? This is something known as the twin paradox, which isn't really a paradox, but that's what it's called. We'll get to some things later that really are paradoxes, but this isn't one of them. So this is showing, two twins who start out the same age. The other twin goes on a rocket, comes back. He hasn't aged much at all, but the twin that was left on Earth is a lot older. So that's Einstein's twin paradox. For those of you who've seen the movie Interstellar, there's another way to do this. In that movie, slight spoiler alert, they go and park near a black hole and then come back, and they've got a similar effect of their clock was moving slowly while they were parked near the black hole, while lots more time passed on Earth. So there's a different but related time dilation effect associated with a lot of gravity, which is produced by black holes. So time travel to the future, at least in principle, if someone can make me a rocket ship that goes, a good fraction of the speed of light, you can do that. So before I get to time travel to the past, I have to go through a lot of other shenanigans with you here. So let me talk about how space gets changed in Einstein's special relativity. So that object moving in the rocket ship appears to be shorter than it would be if it's at rest. And if you want the formula, this is the formula. But this is a baseball, and this is a baseball going at some large fraction, 87% of the speed of light. What happens as the baseball approaches the speed of light is it becomes less of a ball and more of a pancake. The dimension in the direction it's moving gets squished more and more and more as you go nearer and nearer to the speed of light. So observers moving relative to each other disagree about time intervals, and they disagree about lengths of objects. And what I want to motivate for you, because it's, to my mind, a useful way of thinking about these special relativity issues, is something called the space-time interval. Our physics symbol for that is delta S. Delta means an interval. And this is something upon which all observers agree, whether you're in the rocket ship or in the car or on the ground. And for those of you who are like, it's after 5, I don't do math. There's a little math on the next few slides. You can just kind of hum to yourself or something. And then that'll be it for the math tonight. So the math starts with this guy Pythagoras, right? That you may remember these triangles in high school geometry. So if I want to measure the distance between point A here and point C here, that distance I've labeled with the symbol R, it's related to this side that I've labeled Y and this side that I've labeled X, and this is the Pythagorean theorem that relates the length of the hypotenuse to the distance along the two sides. Okay. Now, if I want to go into 3 dimensions, I'm going to have, you know, a north-south direction, an east-west direction, and an up-down direction, right? So if I want the distance between point A and point B here that are at corners of this parallelogram or whatever this thing is, then I just add that third side, square it, and that gives me this distance R here. Okay. So that's the space interval. Okay, that's the space interval between A and D. R is my space interval. Now what's a space-time interval? Okay. So this is my space-time interval that I was talking about. So observers disagree about the time interval. Observers disagree about the space interval. So you might think, maybe I'll get lucky if I add the 2 together, and maybe then everyone will agree. Well, it turns out if you add the 2 together, the problem gets worse. They disagree even more. But if you subtract the 2, so I snuck in this minus sign on you here, right? Turns out if you subtract the 2, then everyone agrees on what this is. And it would be more slides of annoying math to motivate the minus sign better than that, so I won't inflict that on you. But this is a quantity that everyone agrees on, whether they're in the rocket ship or whether they're in the library. Okay? If you want to give fancy jargon to your friends, this quantity is called a relativistic invariant. So for events taking place at different space coordinates, so we're in a different location in either north-south, east-west, up or down, the time interval will vary with the observer. Okay? So this has to do with time here. What makes this a little scary to physicists at least, maybe you won't find it scary, the time ordering of the events can change. So T2 is event number 2, T1 is the time of event number 1. So if that time interval I was showing on all these slides is positive, sorry, more math, that means that event 1 happens and then later event 2 happens. Okay, so event 2 comes after event 1. If that interval is 0, we say the events were simultaneous, right? They happened at the same time. And if that thing is negative, it means event 2 is in the past of event 1. So if different observers are seeing different time intervals between two events, and if different observers are even seeing the order of the events different, then I think we can take Newton's absolute time and kind of throw it out the window. That's one of the few cases where I think physics has settled part of a philosophical argument, right? We can say at least Newton's idea of absolute time just is not consistent with the laws of physics as we know them. So we can replace the question of is time real that I had on my slide with Newton's face with the question, is space-time real? This conglomeration of space and time that Einstein put together. And I'm going to worry about causality here, right? Causality means something happens that causes something else to happen, right? My phone rings, so I go answer the phone. Okay? The phone ringing caused me to answer the phone. So causally connected means that the earlier event could conceivably be the cause of the later event. The phone ringing could conceivably be the cause of my answering the phone. In special relativity, two events can only be connected in that way, cause and effect, if you can get from one event to the other at the speed of light or slower. Okay. So I'll explain this diagram in a second here. So this is known as a light cone diagram. So in terms of our space-time interval, and this diagram is really why I wanted to talk to you about space-time intervals, we can decide whether two events on this diagram could be cause and effect or not. Okay, so in this diagram, you are here. Okay, this is the present time and your location. Things that are this way are in your future, and things that are this way are in your past. Okay. So this is now, this is your future, this is your past. And then if we go this way, we're moving around in space. So we've left the library and we've gone to Mass Street or something. Okay. So things that are within this region here, where the point B is, are allowed to be connected to me in a cause-effect relation. So this could be, my phone rings, and this could be I answer the phone. Happens at some later time, but it's allowed for A to influence B. So events in there have what's known, if you want more physics jargon, a time-like connection. So anything where that space-time interval squared is positive has a time-like connection, and events A and B can be related in a cause-effect relationship. A and C, though, because it's outside the light cone, so this is the boundary of my light cone. Along here, this is things moving away from me at the speed of light. Okay, so if I start at A and shine my laser pointer follows this path into the future. This is something that can't be connected to me because it's got a space-time interval that's negative. Okay? If your space-time interval is negative, that means different observers can see those two events happening in a different order. So I might see event A happen first and event C happen second, but you and your rocket ship, you might see this happen first and this happen second. So if people are disagreeing on which one happened first, wow, how can those be connected to each other as a cause and effect? And physicists just say, that can't happen. Okay, so this leads me to a possible philosophical stance called block time. Past, present, and future are all real. We have a block of space-time consisting of space-time points and some measure of how they're connected to each other. Okay, this is a little jargony here, sorry. So in Einstein's block universe, there's some series of events that we say are all happening at the same time. These are all the simultaneous events, all the things that are happening at 7:30. These are things that are happening in the future. These are things that are happening in the past. Different observers, the observer in that rocket ship, is going to take a different slice through this block. So this is my now slice. This is where I think everything is happening at 7:30. But John, who's traveling away from me, has a now slice that goes like this with respect to my now slice. And Pete, that's traveling towards me, has a now slice that goes like this. Okay? So they think all of these things are happening at the same time. I think this is happening in my future. Okay? So this is Einstein's block time. So now, let me, now that I've kind of armed you with all this stuff, let's go to the question of, what about time travel to the past? So as a physicist, I'm confident in telling you you can travel in time to the future. All you have to do is invent a really cool spaceship. So the philosophy book says these are the 3 questions to ask about this. And they seem like pretty good questions. And of course, the philosopher gives priority to this one. It's like, is it logically possible before we even start talking about the physics? And I kind of have to give him that, okay? If it's not logically possible, then the physics equation shouldn't be able to justify it, right? So let's think first about whether this is logically possible. So let me compare traveling in space with traveling in time for a minute. So to my mind, at least, traveling in space isn't philosophically problematic. You may have had some philosophy class where you sit around going, does Paris exist? I can't see Paris, I can't smell Paris, I can't taste Paris. So, you know, in my solipsistic worldview, perhaps Paris doesn't exist. I'm not going to go there. Paris exists. Let's just say that. There's a picture of Paris. Okay. We can go there if we want. Okay, but let's ask another question. So I'm going to stipulate without philosophical meanderings that 2 different spatial locations can be accessed. So, you know, my right hand is in a different spatial location from my left hand. I can touch 2 different spatial locations. What about this question? Does July 4th, 1776 exist? Does it exist in the sense that I can go there? Does it exist at all? Is it just some idealization? I can't, you know, reach out my right hand and touch a minute from now, and reach out my left hand and touch a minute ago, okay? To my mind, this is a pretty real philosophical question, okay, that's different from the question about two space locations. So two different time locations are not accessible in the same way that the two different space locations are, I contend. So, of course, philosophers write books and lengthy articles about this. There's a view called presentism, which says only the present moment is real, but the past and future are not. Okay? If we adopt this, then we're not time traveling to the past or the future, because only the present is real and there's nothing real to travel to. So for the sake of the rest of this talk, let's not adopt that philosophical stance, but I won't hold it against you if you want to adopt that. Then there's kind of the other extreme is eternalism, which is that all of these things exist and are real. And this fits with that view of block time that I was giving you earlier. And that has some philosophical consequences of determinism that I'll touch on in a minute. So just so we can move forward, let's assume that the past is real in the sense that it even makes sense to talk about traveling to the past. So we've agreed that the past is something that maybe we could travel to, but then real paradoxes arise, not the twin paradox that I claim isn't a paradox at all, but here's probably the most famous of the time travel paradoxes. You travel back in time, and I can't figure out for the life of me why anyone would do this, but inexplicably you decide to shoot your grandfather, okay? And of course the consequence of this is that you were never born, right, because you shot your grandfather, and so the paradox is if you were never born, how is it that you went back in time and shot your grandfather? Cause and effect just are all jumbled up in a hopeless mess. This problem, the grandfather paradox, is solved if we adopt that block time point of view. In the block time point of view, the past is real and the past is fixed. Whatever happened in the past happened in the past, and you're not going to change it. So you can go back in time, but you can't shoot your grandfather because you didn't. Tenses become really annoying when you're talking about this stuff. So the cost of adopting this philosophical stance, okay, this allows us to logically proceed with time travel. We didn't generate something ridiculous. But the cost of accepting that is determinism, meaning whatever you do isn't gonna, you can't change anything. Everything is determined. That brings into question free will and all of these big questions, right? There's another way out of the grandfather paradox that you can decide which one has a higher price. The other way out is this many worlds idea that, yeah, you can go back and kill your grandfather, and what you did there was you created another universe, okay? You were born in this universe, you went back and killed your grandfather, and now there's a different universe where your grandfather didn't exist. So the cost of this is, you know, if time travelers are running amok back there, there could be potentially infinitely many universes where time travelers are doing random things and causing changes to our space-time continuum. Okay? So that also has a philosophical cost. Let me see if I can bring up Brilliant Miles without crashing my computer like I was doing earlier. Okay, so for those of you who didn't watch every episode of Lost religiously, like I did, this is a scene from somewhere in the middle of the series where some of the characters have gone back in time and they've set up a potential grandfather paradox, because another character that you don't see in this scene has been shot and might die, and if that character dies, then that means that events that happen further on would never have happened, and so you wind up in some horrible paradox. So we'll let these two characters from Lost argue about what's going on here.
What the hell are you doing, Toby?
Checking to see if I'm disappearing.
What?
Back to the future, man. We came back in time to the island and changed stuff. So if little Ben dies, he'll never grow up to be Big Ben, who's the one who made us come back here in the first place. Which means we can't be here, and therefore, dude, we don't exist.
You're an idiot.
Am I?
Yeah, it doesn't work like that. You can't change anything. Your maniac Iraqi buddy shot Linus. That is what always happened. It's just, we never experienced how it all turns out.
That was really confusing.
Yeah, well, get used to it. But the good news is that Linus didn't die. So that means the kid can't either. He'll be fine.
Didn't look like he was going to be fine. What if you're wrong?
Well, if I'm wrong, then I guess we all stop existing and none of it matters anyway, then, does it?
Let me get this straight. All this already happened.
Yes.
So this conversation we're having right now, we already had it.
Yes?
Then what am I going to say next?
I don't know.
Ah! Then your theory is wrong.
For the 1,000th time, you think that. The conversation already happened, but not for you and me. For you and me, it's happening right now.
Okay, answer me this. If all this already happened to me, then why don't I remember any of it?
Because once Ben turned that wheel, time isn't a straight line for us anymore. Our experiences in the past and the future occurred before these experiences right now.
Say that again?
Okay. I'm sure that cleared everything up for everyone. Feedback. Okay. So it turns out that, you know, this is the stuff of science fiction, obviously, but there are working philosophers that publish papers on this stuff. My thanks to my philosophy colleague who sent me this paper, which is talking about whether backwards time travel is logically possible because of the grandfather paradox. He argues that backwards time travel does not entail unusual numbers of coincidences, and that even if it did, would not render its occurrence unlikely. So the bananas part is you go back in time and try to shoot your grandfather, but you slip on a banana peel. Okay. And then some philosophers argue, well, doesn't that involve like an infinite number of banana peels, potentially, that you might have to slip on? So he's addressing that argument. This stuff also gets published in physics journals. This is an article from a recent physics journal about quantum mechanical grandfather paradoxes and how you might resolve them. Okay, you'll see the phrase closed time-like curve in here and in the abstract. That's physics jargon for time travel to the past. There's other fun paradoxes. There's one called the bilking paradox that involves you, say, contacting your past self with a winning lottery number. I'll say a little more on that later. Then there's the where are all the time travelers paradox. You may have heard that Stephen Hawking held a party for time travelers, and he sent out the invitations after the party. Nobody showed up at the party, so he's using that to argue that there's no time travelers. The other thing that you can think about is time tourism. So Robert Silverberg has a very wacky novel called Up the Line, in which the main character is a tour guide for time travelers. And he takes his tour groups to see the crowning of a Byzantine emperor. And then he keeps running into himself and his previous tour groups when he goes back there to see that event. And he keeps having to move around to different locations. And the paradox is ultimately this place is going to fill up with time travelers, right? Maybe an American example would be, July 4th, 1776. You want to go see the signing of the Declaration of Independence. And once time travel was invented, that room just fills up with time tourists looking to see what happens there. So my conclusion after all of that is, yes, with several possible, many possible objections, let's say it's logically possible under certain conditions to travel to the past. But what about the laws of physics? Let's go back to the light cone. In special relativity, time travel to the past is impossible. Why? You have to go through the forbidden region of this diagram. So if I want to travel to the past, I have to follow some kind of loop like this, and that takes me through the forbidden zone, okay? I can't go there. So according to special relativity, I can't do this, but as we'll see, Einstein's other theory of relativity, general relativity, may come to the rescue. I should mention a loophole in special relativity before I go on to general relativity. The loophole is this: you can't get anything moving faster than the speed of light if it started out slower than the speed of light. On the other hand, if the particle or the object originated going faster than the speed of light, that's okay. However, it can never go slower than the speed of light. It always has to go faster than the speed of light. These hypothetical particles are called tachyons. They would travel space-like paths, which means they could go backwards in time. And in fact, science fiction writers have used this. There's a well-known novel by Gregory Benford called Timescape, where some physicists make a tachyon beam and send a message to people in the past about how the Earth is going to hell and they should do something about it. So that's a loophole in special relativity. That doesn't help you travel to the past, right? That just helps you perhaps send a message to the past. Okay, so Einstein again. That special relativity theory I've been going on about only considers motion with a constant velocity. If you want to talk about motion where the velocity is changing, if you want to talk about accelerated motion, that's where general relativity comes in. And in that theory, accelerated motion gets related to gravity. Now, special relativity is often covered in intro physics because the only math you need for it is algebra. I showed you some of the algebra. General relativity, you need something called differential geometry. The math is hair-raising. Took Einstein a long time to get around the math. Once you do this math, what you find is that massive objects like the Earth or the Sun distort space and time. And it's this distortion of space and time that create gravity, because it affects the motion of objects, because you've warped space and time. And so gravity is explained in this theory as a result of space and time getting warped. Okay, so let me make a cone here. Okay, so here's my light cone. So in special relativity, you always have to move towards the future in your light cone. What can happen in general relativity is space and time can warp, and that can make your cone tilt. So if your cone tilts all the way over, then all of a sudden, what used to be you're heading to the future is now you're heading to the past. So in general relativity, you can do this, but it's not easy. So the first person to find a solution to Einstein's horrendously messy general relativity equations that involved a closed time-like curve, remember that's physics jargon for travel to the past, is Kurt Gödel, who you've probably heard about from mathematical fame. His solution involved a rotating universe. So you just take the whole universe and you start it rotating really fast. And in that rotating universe, these little light cones tip over, and you can make paths for the time traveler to go into the past. So that would seem like good news for the time traveler. So indications are, we can look at the universe, right? There's astronomers that do these things and decide whether the universe is actually rotating. So it looks like it's not rotating, and even if it is rotating, it's rotating really slowly and not nearly fast enough for us to have Kurt Gödel's path to the past. Okay. But wait, all is not lost. What if instead of the universe rotating, we have something else rotating? Have the universe sit still and have something else rotate. So a physicist named Frank Tipler, you can read all about it in this paper here, imagine an infinitely long, that's what he means by sufficiently large, is infinitely long, rotating cylinder. And that rotating cylinder will warp space and time around it and make your little light cone tip over, and you can go around to the past. So this infinitely long rotating cylinder also has to be super dense, like 10 to the 40th power times denser than the densest matter that we know about. So a little problem there, but at least on paper, you can go to the past. Here's another solution. I named Richard Gott. Imagine cosmic string. So what's a cosmic string? So imagine like the universe is a piece of glass and it's got a crack in it. Okay? So this is like a crack in space-time, a discontinuity that somehow got formed because, I don't know, it didn't cool properly when it was forming or something. So if you have one of these hypothetical defects in space and time, in fact, not just one of them, but two of them, and they're moving at near light speed, then you can get some nice little loops around these cosmic strings and you can travel into the past. Okay. And then here's everyone's favorite, this is what they do in Interstellar, right? Wormholes. It's a bridge connecting two different locations in space-time. So if there's a wormhole that has a time difference between the two ends of it, so say this one's at a present time, this one's at a future time, you can play games going in and out of the wormhole and go back in time. Okay? So people have even thought about wormhole engineering. Okay? How do I do this? Here's a paper, Kip Thorne, by the way, was the science advisor for Interstellar. This is one of his papers. How do we make this wormhole so we can have a time machine? Well, first, take a microscopic wormhole and make it bigger. In theory, there's microscopic wormholes all around us. No one's ever confirmed that, but theoretically, there's microscopic wormholes all around us. So just grab a hold of one and make it bigger. Okay, step one, easy, right? Step two, you have to stabilize it so these microscopic wormholes appear and disappear like instantaneously. So you not only have to make it bigger, you have to make it stick around. And they figured out how to do this. All you need is a supply of exotic matter that has negative energy that no one's ever seen or observed. But theoretically, if you had such a thing, you could stabilize your wormhole with it. Now the next thing is you have to make it big enough, because you don't want to get spaghettified. But this is my favorite word in relation to wormholes and black holes. So what do I mean by this? Okay, so I'm standing here on the surface of the Earth, and the force of gravity at my feet is a tiny bit bigger than the force of gravity at my head. It's a really, really super tiny difference, so it doesn't bother me any. But the force of gravity changes as we go up away from the center of the Earth. Okay? Now, if you have a super dense thing like a wormhole or a black hole, this change in the force of gravity happens over a distance as big as me. Okay? So if the force of gravity at my feet is like a zillion tons bigger than the force of gravity at my head, what happens to me? I get spaghettified. I get stretched out into a nice thin line, and I will not be happy about this. So in order to avoid getting spaghettified, you have to make the size of the wormhole big enough, or else you really don't want to go down it. They figured out that all it would take is the energy output of a star over about 10 billion years. That's the amount of energy it would need to make the mouth of the wormhole at least a meter wide. Okay, so you don't get spaghettified. Last step, and so help me, this one seems like the easy one. Move one end of the wormhole to a different time. So just take one end of the wormhole and accelerate it. And now you've got a time machine. Okay. So is it logically possible? I think we all agree that in some philosophical stances it's logically possible. Is it physically possible? Well, it hasn't been definitively ruled out. Is it practically possible? Looks pretty impossible. Maybe somewhere some aliens have already made a traversable wormhole, or maybe nature made one for us, but I don't know how to make one of those things myself. So let me conclude with returning to the bilking paradox, which I promised you I would return to. Here's how the physics lecture bilking paradox works. Pick up your cell phone that emits tachyons, okay? So you can communicate with yourself an hour ago. Okay? Give yourself a call, talk to that past self of yours, and warn your past self not to come to this lecture. For God's sake, don't go to that lecture. Your past self heeds the warning. You trust yourself, you trust your advice, right? You don't go to the physics lecture, you do something worthwhile instead. And so, because you didn't go to the lecture, you never make that phone call to your past self to warn yourself. So where did the warning come from? That's the bilking paradox. Thank you all for coming. Any comments?